All right, thanks, Mama, for the nice introduction. And hi, everybody. Thanks for coming to the talk. Today, I'm going to talk about collective and multi-relational models for network data. As you all know, networks and graphs are everywhere. We got social networks, pharmaceutical and biological networks. We got scholarly networks like co-authorships and citations, World Wide Web, the internet, you name it. Almost any kind of data that we collect these days, we could put it in a network form. But usually, real-world networks are heterogeneous and multimodal. That means they have different kind of links, and each link, different kind of nodes, and each node type could have different features. And they're also multi-relational. That means nodes have different kind of links between them, and they have features as well. But usually, traditional network models are very simplistic, that they ignore these kind of information. The other thing is, usually the predictive tasks on network data are using traditional machine learning methods that have IID assumptions, and they agree the interdependencies between the unknown variables. In contrast, collective models make joint inferences about these. Having these two perspectives in mind, I'm going to talk about two major tasks in network mining. One is node classification. The other one is link prediction and regression. I'm going to motivate the node classification with social spammer detection and motivate the link prediction and regression with pharmaceutical discoveries and recommender systems. So, jumping right into node classification, I'm going to start with a simple experiment showing some examples of how effective it is to consider the multi-relationality of the network versus not considering this. And as I said, I'm going to use social spam to motivate this. Everybody knows social spam is a problem. For example, Netscape reported that in 2012 to 2013, social spam grew by more than 660%. And it's growing faster and more than good comments in the networks. One of the reasons for this is there are more ways for spammers to get to users. They're easier to find, and they can split their content, spammy content, into different channels and bypass content filters. So to more clearly specify the tasks that we want to do, so we have a network of users shown by nodes. Each are partially labeled. Some of them are spammers, some of them not. And we want to find out the labels of the other spammers. The actions between the users are links in this network. They're time-stamped, and they have different types. The different types could be messages, friend requests, profile review, report abuse, and so on. And our task is to label new spammers given the previous labels and also the structure of the network. And since spammers are sophisticated and they can bypass content-based filters, we want to figure out how much signal is only in the network structure that we can add it later on to content-based filters. And also, sometimes the content is not available due to privacy reasons. So the data set we got is from tag.com, it's a social network with about 300 million users. The sample we got was about 5.6 million users, about 1 billion interactions with 10 different types. And 4% of them were manually labeled as spammers. And remember, this data is coming from a live system, so they already had a content-based filter. This 4% spammers had to be manually identified by the security team, and they were more sophisticated spammers. So the first thing we tried was getting a vector representation or a vector feature for each user. And what we did based on this multi-relational network, we got different subgraphs out of them. And for each subgraph, we computed graph analytics features on this subgraph and then used each of them as a feature. So we had 8 different subgraphs and 10 different features. And then we put it into a standard classifier gradient boosted tree. And you can see that there is a signal there that of a area under the precision recall of 0.32. And that is only using the network data and not any content. And the question is, OK, so we can do this, but is it better to extract more features from a single type of relationship? Or is it better to extract a simple feature for more relationships. For example, the spams are in the messages. Should we only concentrate on our messages and extract different features, or get more relationships like profile view and other stuff in there as well? You can see that using a simple feature on different kind of relationships is better than using more complex features on only a single type of relationships. So you can see here that this multi-relationality helps even in this simple feature extraction method. So getting back to our story, the multi-relational nature, even if you want to do simple feature extractions from the network graph, from the network structure, it gives us potentially better structure features. The second thing we tried was based on the assumption that the spammers account are not really human beings, and they are software. So if they're software, their behavior should be similar to each other, and we can actually capture this behavior because we have multi-relational links here, and we have the timestamp, so we could see the sequence of generating these links. For example, the user sends a message, does a profile view, sends a friend request, does another profile view, and this generates a sequence that we could mine and try to find a signal from there. The first thing we tried over here was a simple generative model based on extension of naive Bayes, and you could see that that's labeled being a spammer or not. This is the first link, second link, and so on, and this factorizes to this, and we could compute the joint probability of being a spammer given the sequence, and this will give us some signal at the AUPR of 0.24. But the thing is, this captures the whole signal, that the whole pattern, the sequence pattern that the user generates. We thought that there is some dependency before, there are some variations depending on the interaction that the spammer that makes with the system. So we got shortish sequences on our second try and used a simpler approach for extracting Bigram features from this. For example, a Bigram would be profile view message, message profile view message, and we count that as features for each user, and we put it in a standard classifier, gradient boost and treat again, and you see that we got a better signal because those longer sequences might have some randomness in there. So the next obvious step is to put these features together, and also to show how much these are effective. We just added 2 demographic features, age and gender of the user, to this, and to figure out how effective this approach is. So this is using the graph structure features. This is a precision recall. This is the ROC curve, and this is adding. This is just using the sequence features. This is adding the sequence features and graphs together, and I can't show the demographic features alone because of legal reasons, but it's somewhere around here. But when you add that to this, you get a boost over here. That is because of the behavioral reason. For example, a certain age group and certain gender would behave differently if they're a spammer or not a spammers. And then you can see we can get a very good performance here. And remember, these are the spammers that needed manual labeling. So we can get a recall of more than 0.6 at about precision 0.9. So you could get a lot of signal from this. Okay, so getting back to our story. Using simple multi-relational nature, we could get better graph structure features, and we add timestamp to it. We could get sequence features that none of this is possible using the traditional models of the network. So next thing we want to show here is that making joint inference on the unknown labels over here helps comparing to this traditional IID assumptions. One of the interactions that users could do with each other is a abuse report. They can point to each other and say, this is a spammer. Most people use it correctly, but a lot of people use it for their own personal gain because there's a social game in that social network, so they want to deactivate their opponents. Also, spammers use that to introduce noise. So what we want to do, we want to jointly classify the spammers and infer latent credibility of the users. For example, we want to find out if this guy and this guy is a spammer. If a lot of people reported this person as a spammer, we want to have a higher value of this guy being a spammer, as well as give a higher credibility for these guys. And if there's only one person reporting this one as a spammer, the score of this being the spammer is lower, and also the credibility of this person is lower. So this is a desired model, and this is a little ham maybe, but so what we want the connectivity between, the interdependency between these variables, and if there are 3 people reporting that, this spammer is high, all the collectivities are the credibilities are high. If there's only one, the spammer is low, the credibility is low as well. So we're going to make that model with probabilistic soft logic, which is the first order logical syntax template language for Hind's Markov random field. I'm pretty sure most folks here are familiar with this. This is like Markov logic networks. I'm going to quickly go over this. So an example template rule for PSL looks like this. You write a logical syntax that if A is credible and A reported B, then B is a spammer. But the left side is called body of the rule, the right side is called header rule, and there's a weight associated with it. The value of these predicates are soft true. That means they're not Boolean. They're between 0 and 1. So the operators have to be relaxed, and PSL uses Lukasiewicz norms for this. This template gets grounded with data. And for example, data is Alice and Bob. So we know the credibility. So let's say we know the credibility of Alice is 0.7 from somewhere. We know Alice reported Bob, so the value of that is 1. Well, we want to infer what's the value of Bob being a spammer. And this will ground some part of the model and connects the credibility with Alice and reported Alice and Bob, and Bob being a spammer. And the potential function here is based on the distance to satisfaction of this rule, and that means it's defined based on value of the body minus value of the head cut off at 0. And the loss here on this value, spammer Bob, if you put in these numbers and this, will look like this. And because this is 1, it says that we know the credibility of Alice should be 0.7, and the value of Bob being a spammer, if it's more than 7, then we incur no loss. If it's less than 7, then we get a linear loss. So, but remember, Bob being a spammer is not only grounded once, it can be grounded more than, it can be in different rules, and there are a lot of interdependencies here. For PSL to infer this value, it will put this potential into this exponential distribution and compute the MP inference on this. So back to our model. So we first start with a simple reports model. And we say, OK, most people are not spammers in the network, because we know only 4% of the people are spammers, so we put a negative prior on this. And the second thing is, just simply if somebody reported, if user 1 reported user 2, then user 2 is a spammer. So this is roughly equal to just counting the number of reports that a person received. This is not collective, very simple. The collective model that we described added the credibility here, and it says, okay, if user 1 is credible and user 1 reported to user 2, then user 2 is a spammer. Also gets a feedback. If user 2 was a spammer and user 1 reported it, then user 1 was credible. And if user 2 was not a spammer, and if user 1 reported user 2, then user 1 is not credible. So you can see that making this joint inference of credibility and the spam actually give us a gain in performance for finding the spammers. Okay, so Moving on, on node classification, we showed some examples of using traditional machine learning methods that multi-relationality help. The second thing, we showed that joint inference help on a single relationship. So this was the node classification for social spam detection. We're going to move on to link prediction and regression. Yes?
Did you try combining those two?
For this one now, but for this one, yes. So I showed that each component actually helps, and then I'm going to combine this one.
Can you show them how for a node for social spammer detection?
Oh, for this one, so that behavior was only based on reports. And reports were a small section of the overall. So out of the 1 billion links that we had, about a couple of 100,000 of them were reports. So,
So you didn't have enough data.
for that. And it didn't, so we tried it and it didn't help that much because this was a very small portion of the network. So okay, let's move on to link prediction and regression. And for this one, we're going to talk about a relational template model that's actually going to use different relationships in the network and makes joint inference based on joint inference for all the links together. For predictions on links, we're going to, if we have binary links on the network, this is usually called link prediction, and it's good for drug-target interaction prediction, protein-protein interaction, friendship prediction of social networks, and citation predictions, and so on. And if we got value for the links, for example, movie and item ratings, this is often called link regression. And we're gonna have a model that actually works for both of these situations. Most of the applications that I'm going to talk about will have this common bipartite structure. That you have one type of node on one side, and I'm sorry I reduced the quality of this picture for PowerPoint not to crash. So we got drugs on one side, targets on the other side. For recommended systems, we got user on one side, items on this side. For image capturing, we have images and text. This bipartite network is common, and for this we have two types of nodes, and we observe some of the links. We want to infer or predict the value of the other links. But usually, this is not the only thing we have. We have more information on the sides. For example, we have features for the users, or we have features for the items. Or we have features on the links. For example, if this is recommender systems, we have demographic features for the users. We have content features for the movies. Or if, this is, again, if it's recommender systems, we have the context information, for example, time and locations of the ratings. We can have actually relational information between the nodes here. And if these are users, we can observe the connectivity of them on social networks. Or this could be if they share some characteristics. For example, if they are directed by the same director. We could have additional relationships on the original relationship. For example, if this is recommender systems, we want to infer the value of the rating. We can observe that this person already read about this movie, and then add that information in. We can also have additional relations with external nodes. For example, if this is scholarly networks and authors and papers, authors can have interactions with institutions, and papers can have relationships to venues. And we can add that information in. A lot of these structures can be converted to this type. For example, here you could compute the distance. Simple Euclidean distance will give us similarity, and then you can use similarity as a relationship between nodes. For here, you can use the common neighbor, how many common neighbors they have, and extract that, put it into this. For this one, we can use collaborative filtering similarities, and then add similarities to this structure. So we're going to propose the model that mainly works on this, but a lot of these can be converted to that. So the template model that I'm going to talk about have two components. One of this is similarity-based reasoning, and for similarity-based reasoning, it's going to support joint inference for link values and support multiple relationships, and it's going to have priors that can capture distribution characteristics and also can incorporate information from auto models. So the first component, similarity-based link inference, makes a simple assumptions. If two links are similar, their value should be similar. And it will look like this. If link AB is similar to link DC, then their value should be similar. But the question is, how do we define the similarity between link AB and link DC? We simplify that by saying if two ends of the links are similar, then the links are similar. For example, if A is similar to D and B is similar to C, then AB is similar to DC. We have that information. We can do that. A special case of this is when we have this tetrad structure. A special case of this is where we have the triad structure, because every node is similar to itself, so we have similarity of 1 on one side. And this says simply if A is similar to D, then AB is similar to DB. And it can be captured in this. You can see that we can make joint inference with this. We can connect two unknown links together. We can support multiple relationships because we can support multiple similarities here. And priors, we can enforce the sparsity on the network. Say that in this network, I know that a lot of interactions don't exist. So we put a sparsity prior on it. We could put distribution mean or other characteristics of the distribution here. For example, I know the average rating of this person is 0.2. The average rating of this person is 4. So I'll put a prior of 2 for one user, 4 for the other one. I could put predictions from other models here. For example, I ran matrix factorization on it. I already have a prior here. I can add it to the model. Again, we're going to do this with PSL. And this rule simply captures that. It says if link AB is, if we have link AB and similarity BC, we got link AC. This is basically that idea. And if this similarity is 1, let's see what happens. Putting in the norms and the distance to satisfaction, we get something like this. So link AC, if link AC on the right side, if it is higher than link AB, then we'll have no loss. If it is lower, then we'll have a linear loss. But if this is symmetric, if BC, if we got also similarity CB here, so this is a template, remember, so it will ground the other side of it as well. So you will have a loss on this on this side as well. So we'll say if link AC is smaller than link AB, then we're fine. If it's higher, then we'll see a loss. We'll have both of them together, so you can see that there's a loss on two sides of the value of link AB. And what it tries to do, it tries to make the value of link AC similar or close to the value of link AB. This is when the similarity value of BC is 1. But if it's not 1, then we'll have a region around the value. And that will be 1 minus the similarity of BC. For example, if it's 0.9, then we'll have 0.1 around the value of AB, and then we'll start having loss. And that was for the triad structure. For the tetrad structure, each of this will add a flat region. So if this is 0.2, if this is 0.8, if this is 0.9, so the flat region here would be 0.2 plus 0.1, and that's 0.3. And we'll have it on both sides as well. And the priors would look like this. What it does is actually put a linear loss on the value like that. And if we have, this is the sparsity prior. If they have the mean prior or prior of the other models, we can put two various priors on it and enforce the value of link AB to be similar to the prior of AB. So having this template, the first thing we applied it to was drug target interaction predictions. And why is this important? Because new drugs take a decade to reach market. They cost about $2 billion. And if we can predict the value, if we can predict that a drug interacts with a protein target, then we can predict side effects of new drugs that people could go and do wet lab experiments on it. It can be used on precision medicine If this target is coming from a cancer patient, then we can find which drugs are important or effective on that. We could use it for drug purposing. We know that this drug has been approved safe. What are the other applications for it? An example of this is Viagra, which was originally developed for cardiovascular disease and then repurposed and rebranded. So our data looks like this. We know some of the interactions between drugs and targets, and we have similarities between drugs. We have similarities between targets of different types. And then what we want to do, we want to infer to see if there are any other interactions in this network. We use our template. We use the triad basis structures. We use the tetrad basis structures, and only the sparsity priors here. And we tried it on drug bag data set, 5 different similarities between, we extracted these based on different forms, 5 different similarities between drugs, 3 different similarities between targets. And the first question is, which one of these templates that we had for capturing the similarity things between links is more effective? And for this experiment, and also for the other data sets that we did, the triad-based results are better. Perhaps it's because one side of it is restricted, and it's more closer to the evidence. So the second question was really combining different kind of similarities matter or not. So we had, yes?
But the triad-based would achieve what the tetrad-based achieves in 2 steps, right?
The triad-based will achieve what triads? Because of the max, some of that effect will go away. So it's not exactly the same, I think. The tetrad can capture the triad and more, but I think that because it's more loose and it can find any kind of similarity, it will get a little dirty. So this question was combining different similarities, so for this kind of model, we only use one kind of similarity with priors in there, and we saw that putting all the similarities in will significantly improve the results of using only one type of similarity. So the third question is, does the collective prediction matter or not? And how does collective prediction work here? As I said, we can have the link, and we can connect the unknown variables of the links together. And what it means is we can infer the value of this middle link based on the first evidence, and then we can propagate this down and use the value inferred here again. To block this, we can only write a rule that makes predictions based on observed evidence. So this will not happen. Only this will happen. And you can see that the collective version outperforms the non-collective version. So we showed that using multi-similarities works better. Using the joint inference works better. And we compared it to the state-of-the-art method in that domain. We got better results. And this paper got a good attention. It was featured on the cover of IEEE TCBB. So moving on, recently we tried this for drug-drug interaction prediction. Drug-drug interaction predictions are highly important as well. A lot of people take more than one medication at a time, and they can interact and cause adverse effects. It can also be used for synergetic effects. Drug cocktails is something that's being studied actively in this domain for cancer treatment. We used similar model here, and we got state-of-the-art results in that domain as well. And moving on to recommender systems, you can see that we have similar structures in recommender systems. We have users on one side, an item on one side, and relationships on the side. And we got previous ratings, and we want to infer new ratings between a user and an item. Again, we use the triad structure here. And for the similarity between users, we use collaborative filtering, user-based collaborative filtering methods to extract similarities, cosine, Pearson, and we got the cosine between the latent factors after using matrix factorization on this. And just to say, this not only includes similarities, you can have social network connections. And if these two people are connected on social networks, we can add this to be just connected BHC on social network or not. And this side for item-based collaborative filtering, we did again cosine, Pearson and latent cosine. And for content-based, for the different data sets will give us different ways to do this. So we had the tags on one side, people tagged it, and then used that to compute similarities, and we had the categories of items and used that to compute similarities. And we used more priors in this model. We had the mean centering model, which was the average rating of the user. For each user, what's the average rating? That this user is more critical, always gives 0.2. This user gives higher, and we use that. The average rating an item we received, we put it on each of the links that were connected to that item. The average rating of overall in this system was the average rating of the links in that system. We use that. And prediction from auto model, we use predictions from matrix factorization and also item-based collaborative filtering, and we put that in this model. So these are the results from that. This was a paper on Regression last year. So we tried it on Yelp and Last.fm and compared it with traditional collaborative filtering methods, item-based matrix factorization, Bayesian probabilistic matrix factorization, and with also hybrid models that can incorporate more information, and we could achieve the best RMSE on both domains. Okay, so for link prediction and regression, we proposed a relational template model that can make joint inference of link values, and we could support multiple relationships. We could support distribution characteristics of the links, and we could incorporate information from other models. But there's a problem here that I kind of sweep it under the rug right here. If you're extracting the similarities, everybody is similar to everybody. So you'll have a lot of similarities, and if we use all of the similarities, we'll have a lot of groundings. Have a lot of groundings, the inference time will explode, and also it will hurt the results. So what we did for the previous applications, what we used k-most similar items to an item. So for example, for this drug, we only got the k-top similarities and discarded the rest. This is a problem that comes up in many related techniques. For example, in k-nearest neighbors, we choose k and then run our model. For graph-based semi-supervised learning, we learn the neighborhood graph here based on different methods. That the best one is using the k and then run the semi-supervised learning. And this is the same problem with our model as well. So we have to choose the number of neighbors. And so this called a neighborhood graph, and this is usually built by a sequential pruning process. We have all the similarities, prune some of it, and choose k out of it. Challenge here is we have multiple similarities to choose from, and also we can also the unknown variables could be useful as well. So we want to connect that as well. So to more clearly define what the problem is, so we have similarity between variables of different types. And what we want to do is we want to select some of them and put it in the model. And because we don't know which one of these are useful, we want to infer these values while we're selecting the similarity. So we came up with so this is an ongoing work, and I got preliminary results on it. But we came on with an iterative approach that starts by learning the importance of each relationship. So we initialize the neighborhood graph. We learn the importance of each relationship, and then we infer some initial states of the variable. Then we nominate some of the variables to get more similarities for. We could have different heuristics for this. And then for this nominated instance, we could activate some similarities, again, based on some criteria, and then add this to our graph. For example, here and here, these two are added. And then go back, infer again, see what changed, and what needs more similarity, add the similarities, and so on. So we had different heuristics for this. For nomination, we can use the low value and uncertainties. We could use this disagreement in the model. We can use the certainty of high value. For example, I know that this is a link, and if I connect this more to the other things, I can propagate this information to the other variables and use that. For the activation, we could activate based on value or based on nominated instant count or observed instant count. And what does that mean is, for our setting, when we select a similarity, this is shared between a lot of triangles. So we can count how many unknown variables this will activate and how many observed variables this will activate, and use that as a method to select the similarity. So this is, I said, preliminary results on this. And on the left, you can see nominating based on disagreement in the model. And on the right, you can see activating based on observed instant counts. And both of them work better than just looking at the k-nearest neighbors. OK. Which time do I got? OK. So back to link prediction and regression. So we proposed a relational template model. And for that, we came up with an adaptive neighborhood graph construction to actually select similarities for this model. So next, I'm going to briefly talk about this regularized factor model, which factor models, as you know, is a popular method to infer link information from in the industry. And one of these popular methods is factorization machines that can actually incorporate some of the information of the nodes in the model. And sorry about that. So if you have feature space representations for nodes and also links, factorization machines can incorporate that. In contrast with a relational template model, the native representation in our model is relational. The native representation in factorization machines is vectorized. So it looks like this. So the ratings here, which is over here, is coming from this relaxation of polynomial regression. And what they do, based on some clever feature engineering, is they'll have one feature for one user. So each row will correspond to one user, user 1, user 2, user 3. And each row will correspond to one movie. So what this row shows is that user A rated movie TI or T1, and the rating was 5. And over here, they'll learn a latent factor for each of these columns. For each of these columns, which corresponds to one item in your data set. And you can add additional information to these interactions. For example, time could be added like this. There are different ways to do this. One of the most effective ones is this. You could see that what was the time that this interaction happened. It was 1 a.m., 2 a.m., 3 a.m., 4 a.m. So what we wanted to do is to capture some of the domain knowledge between the factors. For example, if we know 10 a.m. is close to 11 a.m., and there's no way for the model to know that these factors should be close to each other. And what this helps is just naively giving an example. For example, I know that someone comes in at 10 a.m. It gets coffee. All my data set, training data set, is based on 10 a.m. and I know it's 10 a.m. That person needs a coffee or likes a coffee. If it's 11 a.m. and someday he comes back at 11 or 12 a.m., we don't know that 11 a.m. is, the model doesn't know that 11 a.m. is close to 10 a.m., so it cannot use that information. So what we did was actually incorporate that domain knowledge to making these factors close to each other. The factor of 11 a.m. Becoming close to 10 a.m. And then we use that on Yahoo Music dataset. And we can see that this is actually effective in improving the results. So I think I'm going to finish 5 minutes ahead of time. But what we did, we talked about node classification and using social spam detections. We use a feature-based method with multiple relationships, and we showed that in feature extractions both of them matter. We showed that using one single relationship, joint inference matters. We then talked about link prediction and regression, and we did it based on pharmaceutical discoveries and recommender systems. And we proposed a multi-relational and collective template for link inference. We used multiple similarities on it and showed joint inference matters on it. And then we talked about adaptive neighborhood graph constructions for this model to fetch similarities based on the state of the model. And then at the end, we talked about a regularized factor model that could actually help with factor models. All right, that's all. Thank you.